Hi, welcome to Chem 40C. Um, Welcome to the new quarter. I hope your fall quarter went well. If you all don't know who I am, it's nice to meet you. My name is Emmanuel. I'm a third year studying pharmacological chemistry, and I'm hoping to do a minor in general biology, but we'll see how that goes. And I really like organic chemistry. I think that I um, have a good understanding of the subject thanks to amazing teachers such as Godula, which most of you might be taking. And I also had the privilege of taking Professor Wiseman during fall quarter of my last year when everything was okay. So in an effort to try and uh, make you all like organic chemistry, and in an effort to pass my knowledge along, especially in such a rough year, such as this school year, I decided to make these videos. And if you need to brush up on your 40B topics, I completely covered the entire 40B except for NMR. But I don't think you're gonna need to know NMR. So your first chapter in 40C will be on carboxylic acids, right? Um, you might have covered this with your 40B teacher, depending on how fast you all were. But it's usually in conjunction with 40B because if you remember, go back a few years or last quarter, depending on when you took it, you learn about carbonyls, right? And carbonyls were these compounds with a carbon that is double bonded to an oxygen, right? And that had you did a lot of reactions with that, including aldol condensation, where you took away an H2O, made new bonds, and you did Robinson annihilation, where you made a new ring, right? Because of the 1,4 addition and the enolate compound. And you were also doing a lot of, you were also doing a lot of like oxidation and reduction, right? So these compounds are very, very important in organic chemistry because of that. So now we're just adding on to that, where now instead of a carbonyl compound with just a ketone or an aldehyde, we have this extra OH group. And that's going to allow us to do a lot more um, chemistry than just a ketone or an aldehyde, right? So, for example, carboxylic acids in the name suggests that they are acids, right? And acids have an acidic proton in the form of an H. And in this case, the H will be the one that is attached to this oxygen because, as you know, it's a dipole moment. Oxygen is way more electronegative than H, which means H has a delta positive, right? And we can denote that here, delta positive and delta negative. And we can actually numerically derive how acidic that H is. And lucky for you, we don't have to do. We just have to look at it in the table where the pKa is around 3.55. So the lower the pKa, the more acidic the molecule is, right? So if we actually take a look at it in a more theoretical way, if we take away this H, we can see that we get a negative oxygen, but there is the possibility of our good old friend resonance, right? And you learned in 40A and 40B that things that make good acids are um, stabilized and stable conjugate bases, right? So conjugate bases just means you're taking away that H. And in this case, this is stabilized through resonance. And because it's stabilized through resonance, that makes this a stable conjugate base of a carboxylic acid, right? So along the fact that we have this huge dipole, we are also given, and we can see that the conjugate base has been um, stabilized through resonance, which means that it's a good base, a good acid. This carboxylic acid is a good acid, as the name suggests, right? And this compound over here actually has a name for it. It's called a carboxylate ion. So these play an important part in our body. And these are found in a lot of amino acids because of the fact that they have this negative charge over here, and they have the ability of electrostatic interaction as well as dipole-dipole or ion-dipole interactions, right? So again, carboxylate ions, right? And actually, how acidic this H can be altered. So it can be more acidic or it can be less acidic, right? Depending on what situation you want it to be. So let's take a look at where this side over here is an R group, right? It can be any group. In this case, let's have it be a methyl, right? CH3. And let's have it compared to a carbon with an electronegative element such as chlorine involved, right? So in these two cases, do you think the H here will be more or less acidic, right? More acidic means the pKa will be lower. Less acidic means that the pKa will be higher, right? So think back. This actually covers your one of my favorite chapters in aromaticity and benzenes. If you think back, you learn about electron donating groups, or as we like to call them, EDG, or we can also think of it as electron withdrawing groups, right? EWG. And you can start to see it here, which one will be donating and which one will be withdrawing, right? So this CH3 compound, this methyl, will actually donate because if we take a look at the um, polarities, carbon is way more electronegative than H, right? So carbon will have a huge delta negative, which means it's going to be donating, right? It's going to be donating, I shouldn't put a dipole there. It's going to be donating electron density in terms of inductive effect to this H over here, making it less, making it more, or sorry, making it less acidic, right? Whereas if we have it in the form of chlorine over here, carbon compared to chlorine, chlorine has more pull, right? So this chlorine will actually be taking not only the electron density of this carbon, but it's also going to be taking the whole electron density of this entire molecule, making this H easier to take, meaning it's going to be more acidic, right? And we can actually see these in the pKa's, right? So if we compare it to the top where we had the pKa is around 3.55, if this is an H, if this is a carbon, the pKa is around 4.76. And if it's a carbon attached to an electronegative element such as a halogen, it's around 2.82, right? So that acidity can be altered, okay? And let's move on to how we actually make these carboxylic acids. So in 40A and 40B, you learned about oxidation and reduction, right? In 40A, you focused on alcohols, while in 40B, you focus on carbonyls. And you can actually oxidize a primary alcohol, right? Because secondary alcohols oxidize into ketones. You can either oxidize a primary alcohol or an aldehyde, right? And if you use this CrO3 H2SO4 underwater, if you remember this chromium species, it's called a Jones reagent, right? So if we use a Jones reagent, we can fully oxidize a primary alcohol into what we want, our carboxylic acid, right? And this aldehyde will also work if we use a Jones reagent, right? So let's learn the mechanism. Here we have this CrO3, right? But we actually skipped some steps and we reacted it with this H2SO4. But this is the molecule that you need to know, right? This has a huge electro dipole positive over here, which allows our OH to attack this H and have a positively charged O, right? As this positively charged O occurs, the O negative will attack the carbon, and at that same time, in an SN2 type reaction, the water will leave, right? Once that water leaves, we're left with this molecule over here, okay? And then once we have this molecule, let's think about the electronegativity and the dipole moments of this molecule, right? Here we have a dipole negative. Here we also have a dipole negative, and here we also have a dipole negative. Chromium is a dipole positive, right? But you can see how there's a lot of dipole negatives, right? And what that's actually causing is that it's causing this carbon, these H's are becoming more acidic. They're becoming easier to pull off because of that, right? So because they're becoming easier to pull off, we can pull one of the H's off, right? This water compound has enough electronegativity to attack the H because again of these dipole negatives over here. As it does that, this double bond will move over to that oxygen, right? And then the CrOH will leave. Okay. And then what do we get when that happens? We get this compound, right? And if I draw this in a better way, it actually is our aldehyde, right? And also, now that we have this, we can further on react this because now we are still in acidic conditions, right? Now we're in acidic conditions. And then you can actually do some chemistry. I suggest you try this on by yourself, but we proved that we can, one, we oxidize a primary alcohol into an aldehyde, right? If we do that one more time, we turn it into a carboxylic acid, right? So now I'm still in acidic conditions and I still have water, right? So if we do this reaction further, we're actually going to make our carboxylic acid. And you might be able to see that here, but I suggest you try to do the reaction by yourself at home, okay? Our second way is with a carbon dioxide molecule, right? So let's take a look at this molecule first, right? This is a CO2 molecule. Carbon is less electronegative than these oxygens, which means oxygen is going to pull on the electrons a bit more, right? If it pulls the electrons a bit more, here we have a delta negative, and here we have a delta negative. The carbon is the carbon electrons are being pulled by both oxygens. So that means there's a huge delta positive here, right? And you can sort of see our carboxylic acid here, right? To remind you, this is what our carboxylic acid looks like. We just need, well, one of these double bonds to go away, and we need to add that H onto there, right? And we can actually react these with our favorite friend that you all love, I'm pretty sure, are Grignards, right? Grignards are really, really strong. So that means if they're strong nucleophiles, we can attack this carbon because it has a huge delta positive, right? And then if we do that, sorry, let me look at my notes real quick as it's been a while since I've taken this class, right? So if we do that, we can attack it over here. Then the double bond will move over to that oxygen, right? And then once that happens, here we have, this is bonded to an O, and then this is bonded to the O that was negatively charged, right? And then here we have 1, 2. Since we're adding a carbon, we have 1, 2, 3, right? So I hope that makes sense. And then now we can also do, we're almost there to our carboxylic acid, right? And we can also fully react this with an acidic workup, right? And you saw this when we were reducing our carbonyls. So if we do an acidic workup, we can use any acid we want. I'll just use a H3O compound over here. We can take the acidic H, and now we're left with a carboxylic acid, right? OH. So what we did is we took a carbon dioxide molecule, we reacted it with a Grignard. This can either be MgBr or an alkyl lithium, right? Depending on which one you want to use. And then we do some chemistry with that. We attacked the carbon because it was delta positive. The double bond moved up to the oxygen. As that happens, that oxygen now becomes negatively charged. And if we do an acidic workup, we can get our carboxylic acid over here, right? The next step is with a nitrile, right? So a nitrile is anything that has this C triple bonded N, right? So in this step, we have a NaCN, and here we have a haloalkane, right? So think back to 40A, where you learn about this. This is actually an SN2 reaction. So what happens in the SN2 reaction? It's a backside attack. It happens in one step, right? It's going to attack the carbon and the Br will leave. As that happens, we have our nitrile compound right here, right? This is called a nitrile. And then if you do some chemistry, you react with this nitrile with under acidic conditions, right? H3O. You will come up with you'll actually get what we call an amide, right? This is an amide. Here we have a carbon double bonded to an O, which is with an NH2 compound, right? And then if you actually react that further, right? If we react this further with an acid, right? With an acid again, we are actually going to get a carboxylic acid. Okay, so I suggest you do this reaction at home too, because I think this is a good way to one, not only review 40B material, but it also allows you to understand where you are in terms of understanding these concepts, right? So I do have a tip. You see that in this molecule, this nitrogen has lone pairs, right? And we have lone pairs with an acid, right? And then in this step, here we have a delta negative, and here we have an acid. So you can sort of see where that's going to happen. And then we're going to turn this carboxylic acid, and then we're going to get, this might help you even further, an NH4 ammonium ion at the end. Okay, so I suggest you do that at home. I will post the mechanism onto the Discord if I have time. Okay. So talking about all these are just the few ways that you can prepare carboxylic acids, but we're not really interested in these carboxylic acids because they're pretty boring, right? To be honest with you, they're not really that fun. Like, you see them in vinegar, but they're not really that fun. What's actually more fun about these carboxylic acids is that you can make derivatives out of them, right? So they're derivatives for this type of compound, which is it's a carbonyl with a halogen, right? So this is a little bit more reactive. So these are called halides of carboxylic acids. And here we can even turn them into these weird compounds where we have what seems like two esters, right? But these are actually called anhydrides. Anhydrides. And then these are called halides of Ca, carboxylic acid. And we can even turn them into this, which is, if you remember your functional groups, this is called an ester, right? If you've taken Chem 43A before, we actually did this reaction in a lab, right? It's called an esterification. We started with the carboxylic acid, we reacted it with water or something containing water under acidic conditions, and we actually get this ester. And then we can even turn them into this, which we saw up here, right? We turn them into these amides. So this is called amides. right? So in coming up in your next chapter, so that was all. Um, that was chapter uh 19. That was carboxylic acids, right? You learn how to make them. You we're gonna learn reactions with them, but we're actually more focused on these carboxylic acid derivatives, right? And we'll actually see these in the next coming chapter. Okay. I hope this was able to help. Good luck with studying, and if you need anything, I'll be here. Okay. Have a good one.